Okay, for time's sake, we're going to go ahead and get started. Welcome to the See the Light webinar today that's given by Art King, and with our guest here with Sharice Nagaraj. We're happy to have you. We're glad you signed up. Please look on our website for more to come. I'll go ahead and introduce Art and Sharice so we can go ahead and get started. Art is a part of our IBN technology team. He leads the development enterprise services definitions and business case propositions for customers and partners. He's the vice chair of the services working group in the Small Cell Forum. And he came to Corning from Spider Cloud Wireless, and it formerly led the IT architecture and operations for Nike Incorporated, where he held various global roles for over 10 years. Prior to Nike, he led the build of 2 multinational engineering and consulting organizations for an IP service network vendor in the service provider industry. Also today is Sharice Nagaraj, and he is our chief technologist in our wireless department here at Corning Optical Communications, and he leads the 5G RAN development for in-building networks. Prior to Corning, he was with Intel, driving early wave technology adoption. He also worked at Nokia, Motorola, and Lucent Technology Bell Labs in their advanced networking technology and research divisions, developing cutting-edge concepts such as cloud centralized RAN, massive MIMO, inter-cell cooperation, coordination and interface suppressions, as well as early forays into layering the use of advanced machine learning algorithms and data analytics in RAN planning and optimization, if that is not a mouthful. We would like to welcome everybody, and Art, please take it away, and thank you again, and welcome.
Okay, Elizabeth, the next slide, please. And welcome, everybody. The goal of this is really to help explain what 5G is. In many ways, the conversation in the industry is about what 5G will do, but not so much about what's under the covers inside 5G. And this webinar is kind of targeted at trying to explain what's under the covers, and in a way that enterprise IT and other people that aren't from a technology perspective can understand. And I have a message up here from Laura Schofield that says she can't see the slides. Oh, now I can. Okay, good, Laura. The flow of the webinar here is a kind of an orientation to cellular terminology, so that if Sharice and I go into the language that we use within cellular, that if you're from the enterprise world, you can definitely follow along. And we're going to talk about the benefits, the goals that are supposed to support those benefits, and the 4 new kind of base group of technologies that are introduced in 5G that will help meet all those goals. And while we're going through it, we'll also kind of talk about where we're at in 2020. And we're watching the question panel for questions as they come in, and we'll take things both in stream and also kind of at the end. Next slide, please. Thank you. So real quickly, in the cellular network, most of the activity right now is in what's called the radio access network, the RAN. So the 5G construction going out in the field with the various different 5G deployments is mostly focused on the radio access network. And for the benefit of the IT folks, the base stations that are deployed are similar to like a wireless controller, and the radios that are deployed are very similar to access points within the Wi-Fi world. And for people that are, you know, well dialed in and have DAS in their enterprise, we'll also kind of touch on DAS infrastructure as part of the orientation. Next, please. So real quickly about 5G and DAS. For those of you who have a DAS, you know, DAS and 5G are going to have a relationship that's going to be operator specific. So, you know, depending on what a mobile operator decides to use for both spectrum and the amount of bandwidth they're going to require, you know, within that spectrum or frequencies, you may or may not you know, leverage your DAS for the delivery of the signal. Many DASs today are capable of carrying the 5G signal. And, you know, should it not be capable, the 5G is going to overlay the DAS if it can't support it. And overlay means that you'll install kind of a parallel network of, you know, radio access points throughout the structure to deliver the 5G in parallel to the LTE infrastructure. And then for sites that don't have a DAS, you know, for instance, Corning makes these small cells and the enterprise RAN. If for any sites that are equipped with that, there'll be a 5G overlay network that runs in parallel to the LTE infrastructure, and the 5G controller and LTE controller will chat together to you know, deliver the 5G service. And then for sites that don't have even small cells, they'll get an LTE plus a 5G installation to enable 5G service. And then just kind of as a note to look into the future, you know, digital distribution where the radios are all digital will eventually provide the multi-operator, multi-frequency coverage. Suresh, do you want to add anything to this slide?
I think that covered it pretty well. Just a couple of things. I mean, in terms of what existing DAS typically supports is like all the FDD bands, the lower bands as we call them. And for some cases, when you go to some of the mid-band spectrum, like 3.5 or 2.5 gigahertz spectrum, it may be that certain DASs may not be capable, but they may get upgraded. And so there is where you have maybe an overlay scenario where you have sort of small cell radios that can capture the 3.5 and 2.5 kind of bands.
Okay, fantastic. Let's see, a question came in between, I guess, web access and 5G. So real quickly, 5G is going to be over the air between the radio and between the cellular radio and the person holding the mobile device or the IoT device. But the back-end network is going to be all fiber. It won't be wired because the 5G network is going to be so fast that it's going to overrun the capacity of copper infrastructure. And we'll touch on that farther on. Next slide, please. So one of the concepts that was introduced in recent, you know, within the last 10 years within cellular is the concept of densification. And you know, while this presentation is applicable to both indoors and outdoor cellular, this is a specifically indoor discussion on this slide. And well, there's small cells going in outdoors also. So densification means that you are going to reuse your spectrum with much smaller cells and get people to fiber as fast as you can. And you know, within the Wi-Fi world, any of you that have done a Wi-Fi design know that you have to get a much denser network when you're designing for voice than when you're designing for just a light-loaded data network. And conceptually here, you know, 5G will have smaller cells, and from a optical perspective, this is what's called a fiber deep strategy, where you're pulling fiber to these radios, so that when you you know, add and overlay your 5G infrastructure, you're going to have the capacity on the transport network behind the radios to carry the massive amount of traffic that's going to be delivered to the radios over the air from the mobile devices.
So Art, maybe one thing to kind of add as well is one of the technologies that 3GPP, which is a standards body for cellular, is looking at is as you go more dense, how do you actually allow for, there may be a fiber access, fiber to a particular access point, but then there's some of the other nodes or radios may be sort of covered with in-band backhaul so that you may actually use the same over-the-air spectrum for some backhaul mesh as well. So that's also another technology that's being considered. But typically, you will have to have fiber runs to support all the capacity, as you said.
Right, right. And Wendell, your question, yes to anything with the NR protocol, and we'll touch on the other three components, or four components that you mentioned as part of stepping through this. So we have you covered. Next slide. So the benefits of 5G, and we'll run through this fairly fast. This triangle kind of shows the various applications and where the services are in the triangle. You have that's kind of a balance of the services they consume. You can see that for the data center at the very top and or the high capacity the system, you've got gigabytes in a second. Low latency is very applicable to self-driving cars, and it's also applicable to things like remote surgery, where you have to have what's called haptic feedback, where when you're cutting, you need to have feedback from the tool on when you're hitting resistance, and so the surgeon can feel things remotely. So it's very critical to have low latency there. And finally, for massive IoT, there's a significant need for the ability to support many more devices than what we've traditionally thought a cellular network would carry in the past. We're at this inflection point where we're anticipating stadium level density in a lot more urban places, and obviously we can't build stadium quality and stadium capacity DAS infrastructure throughout urban areas. So 5G is really a retooling of the various cellular protocols in order to really enable that density to be a native part of the service delivery. Suresh, is on the mobile broadband side, is what are you seeing as far as the demands out there on just the broadband side?
Yeah, so I think a lot of video content delivery. I think that's typically one of the big use cases that would need to be in high definition video is just getting more and more data hungry. And so that's something that we are seeing as a major bottleneck right now that can't be serviced with LTE. So that's kind of driving one of the key use cases there.
Okay, cool. Let's go forward and start talking about we'll touch on the 8 goals of 5G that were defined by the ITU. So next slide. So these are the goals that that were defined by the ITU when 5G was being defined in 2015. And one of the things that's important here, it's a comparison against LTE. So within this radar diagram you see here, IMT advanced was what became LTE. IMT 2020 is essentially what became 5G. And these improvements, when you talk about them, are quite significant. When you look at things like connection density increased by 10, and the area traffic capacity for an individual mobile device being increased by 10. That means that 10 times 10 is 100. So your backhaul, the backhaul, essentially the fiber off the tower or the fiber off the small cell inside the building, needs to carry 10 times the traffic or 100 times the traffic that it used to carry. And you know, there's significant amounts of network that are going to be required underneath 5G in order to deliver the performance to the system that's attached to the cell. And on energy efficiency, want to point out that 5G NR, the new radio protocol, is very, very efficient because it doesn't have a constant signal. So when there's not a lot of network traffic, it actually sleeps and doesn't consume you know, any kind of bandwidth on the infrastructure, and doesn't consume energy to be, you know, radiating. Suresh, you want to make some comments about some of the more important points here under the 5G goals?
Yeah, sure. Yeah, so on network energy efficiency, just picking up on what you were saying, Art, one of the things, if you're familiar with the LTE protocol, is that there are always sort of reference signals and channels that are transmitted always continuously, so that the mobiles can be tracking the base stations and so on. That has changed with the new 5G NR protocol, where there's been a conscious effort to sort of move away from such signals. And what that does is, so you're only doing only as needed kind of signaling. And what that does is basically allows the base stations to go into sleep very fast so that they don't have to transmit signals when there's no traffic going on. And that essentially leads to significant savings in energy itself. And then as far as the other requirements or improvements are concerned, I mean, we'll go through many of the topics here, but there's spectrum efficiency improvements, and, you know, in many respects, we are reaching limits of, you know, what we can achieve in terms of spectrum efficiency, but we are trying to squeeze out every possible improvement with the use of massive MIMO and these sorts of techniques that we'll talk about later. And similarly, as well as looking for opportunities for much higher bandwidth so that we can actually push higher peak data rates. And that also comes with some of the technologies that we'll talk about, like millimeter wave.
Fantastic. Okay, next slide, please. And this is the first of the set of discussing the four kind of core technologies that are underneath 5G, and you know, this is these are significantly important. And right now, a whole lot of the activity has been in RAN. And what's happening with 5G with the new radio spectrum? It's a descendant of the LTE interface, but it has you know, a lot of substantial improvements to it that are almost an outcome of the learning lessons about LTE itself. The maximum spectrum bandwidth for a single channel has went from 20 megahertz on LTE to a full 400 megahertz. So just a huge improvement in the ability to have a wideband signal. And of course, with that ability to deliver a wideband signal, we had to open up frequency ranges in what's called millimeter wave to actually support that wideband signal, because in the lower frequencies, essentially what we call FR1, the frequency range 1 under 6 gigahertz, it's extremely crowded and crammed with all sorts of services right now. And the FR2 initiatives open spectrum above 24 gigahertz so that we could really deliver those wideband high performance services. You know, Suresh, you know, from your perspective, where do you see you know, this going as far as evolution?
Yeah, so there's a constant push to find more spectrum, and recently there were auctions as well that you may have noticed around the C band, CBRS, as well as higher frequencies in millimeter wave. So as you start going towards the right, you start approaching millimeter wave frequencies, technically after 30 gigahertz, but even 24 and 28 are considered millimeter wave now. And it just gets harder to actually communicate on that spectrum, though there is a lot of bandwidth available. And this is basic physics going on there in terms of the waves actually not propagating that well. As you start going down below 6 gigahertz, in the 3 to 6 gigahertz range, that's kind of, if you will, prime spectrum. Now that's getting talked about in terms of CBRS and going forward in C band as well. The sub 1 gigahertz especially is extremely crowded, and you have very limited bands available there. But it's really like prime real estate there. And so there we really need massive improvements in spectral efficiency to be able to squeeze out every bit of bandwidth that we have.
Okay. We have a question from Christian in our audience, and he's asking about why there's no activity between 6 and 24 gigahertz. What prevented the spectral people from allocating something in that particular frequency range from 6 to 24 gigahertz?
That's a good question. So I think that's probably related to existing allocations, as Christian you're referring to here. But essentially, we've got most of the activity around sub 6, which is, and again, 3 to 6 gigahertz, and then going forward in the higher bandwidths. Yeah.
Okay, so basically, pre-existing people that they're occupants of the spectrum, probably especially military uses that won't be moved.
Yeah.
Okay. Next slide, please. Okay, so this is a little bit about how the spectrum is broken down, and from the perspective of the world, you've heard about I think what T-Mobile calls the layer cake, where you can visualize the network as a cake, where the lower layer is propagates a long way and has a certain amount of bandwidth, and the next layer doesn't have the kind of reach, but it has more capacity, and finally the millimeter wave layer, high band, is really has a short reach, but is super high bandwidth. From FR1 midband, those pieces of spectrum are being allocated around the globe to 5G, and where this is going to allow 5G roaming and the ability to go from country to country and roam onto different networks and be able to connect to any 5G network around the world. And Suresh, you want to talk a little bit about what each of these mean and why they're important? And I don't think we need to touch on what FDD and TDD is. I mean, that's a data point, but I think for our audience, we can avoid what FDD and TDD are, but more about what's important about each of these ranges of spectrum.
Sure, I can do that. So when in FR1, again, we intentionally split the FR1 range, which is really sub 6 gigahertz, into two parts. One is low band, which is basically either sub 1 gigahertz, or you can generally call it as sub 3 gigahertz. The spectrum is mostly FDD there. And as I said before, it's really extremely scarce spectrum availability. So in some ways, I look at it as, building something there is like building something in Manhattan, where there's already a lot of crowded areas and so on. And you really have to build tall buildings to fit people. So, if you think fitting bits into that spectrum, you need to have a lot of efficient use of that land, if you will. Um,
I like the analogy.
yeah. So, and then, and what it's good for is, of course, because of the propagation itself, the waves propagate long distances. There's, there are diffractions and so on, and they can actually penetrate even in building and so on. And as a result, it's good for, a lot of IoT applications, especially some sort of a sensor and monitoring kind of applications where things may not be always out in the open, and you need very good link budget to actually reach the cell tower. So those are the kinds of use cases, and it's quite a nice fit because many of those use cases are not heavy on data rates. They may be, waking up once in a while and sending some short burst of packet and then going back to sleep. Um, Except that you do have to serve a lot of such devices. And so that's one of the main areas where the FR1 low band will get used, apart from, of course, voice services currently being used. The FR1 mid band, excuse me, is really again mostly TDD spectrum. CBRS is already out there, 3.5 gigahertz, and that range actually is turning out to be pretty much like a global 5G band. And of course, you do have 2.5 gigahertz as well, which is an important spectrum as well. Um, this is actually somewhere kind of in a good spot in the sense that while propagation is not as great as the low band, but you still have pretty good reach, and you have a decent amount of bandwidth available. So it's about 100 megahertz of spectrum, or a little more than that in some cases. And so you can serve high throughput and high data rate use cases. And what also happens is, and we'll not get into this in too much detail, but when you go to higher spectrum applications, NR has what's known as a scalable numerology. So your slots actually become shorter as well. And so with those shorter slots or smaller duration slots, you can actually achieve lower latency. And so you achieve lower latency, and then with the use of multiple antennas, which we call as massive MIMO in a certain way, which we'll discuss later, you're able to get improved coverage as well. So in a way, this band is trying to get the best of all worlds. Um, and then you have FR2, which is really the high band, and this is 24 and 28 gigahertz and higher, more than that. This is the millimeter wave range of frequencies where, I think of it as, again, the land is not that great, but you have a huge amount of land available. So in a way, you don't have to build tall, skyscrapers there. You just have to, be able to build houses, first of all. So in some sense, if you look at spectral efficiency, going back to the Manhattan analogy, as the height of a building, then you don't need to be very spectrally efficient, but it's difficult to build houses there. And so essentially, the signals don't propagate that well. They don't go through glass and wood and so on. And so now you need to have a lot of, very high density of cell towers and base stations to actually cover that. And so again, antenna arrays come into the picture, which we'll talk about. That's needed for actually coverage and link budget reasons. But you have, it's a very challenging spectrum to actually achieve reliable communications. But that's the place where you have a huge amount of bandwidth available. So the community has been trying to improve core communication technologies to actually be able to communicate in that range of the spectrum.
Okay. So on the FR1, the 5G NR was adaptive slots and ability to have smaller slots in LTE. That's one of the learning lessons taken from LTE with fixed slots, so that you can adapt to the infrastructure. Is that kind of correct?
Yeah, that's correct. So essentially, what happens is as you increase the bandwidth that you have available, the time duration also goes down proportionately. So
Okay.
if you have 100 megahertz a channel versus 20 megahertz, that would be a corresponding decrease in the slot duration as well. So
okay, And on millimeter wave, I understand that it's line of sight, but there's also, I've seen things that show that through bouncing off hard surfaces indoors, you can get quite a lot of coverage to places that cannot directly see the radio. But we'd be able to do densification, but get a lot of coverage through bouncing signals off of other hard surfaces.
No, that's quite right, actually. I mean, one of the common maybe misconceptions is that millimeter wave only works for line of sight. Um, yes, if you do have line of sight, it works very well, but it doesn't mean that it doesn't work otherwise. Definitely reflections actually are a big part of how you get your signal on millimeter wave. What it doesn't do well is actually penetrate through material, like especially glass and coated glass as well as wood and all that. So that's something that you have to plan for. But the other thing is that with reflections, it's something that you really cannot plan for very well sometimes, and so you need some sort of redundancy so that users can be always connected and seeing at least one of two um, base stations or cell towers, if you will.
Got it. Okay. Next slide, please. We'll make this one kind of fast. So in what refarming means, and we put a farmer out in the field here on the slide, so there you go. Refarming means moving one radio technology off of a piece of spectrum and putting a new radio technology on it. So when we moved from 3G to LTE, many pieces of spectrum in the United States had 3G removed and LTE installed. Now with 5G NR can actually fit around the LTE signal and coexist inside the same piece of spectrum, so that in many places the mobile operators won't have to rebuild their networks and refarm their infrastructure. They can actually layer 5G NR into the same piece of spectrum with LTE and avoid a huge project to refarm. Can you talk about the techniques used to, do this, shall we say, fit around, and to kind of not too deep, but just kind of outline it?
Sure. Yeah. So, I mean, one of the things that, like Art, you said, in our specifications, we really taken learnings from LTE, where things were kind of more stiff, if you will, and not easy to change. And one of the big things was this whole idea that you always have these signals that are transmitted, whether you have data or traffic or not. And so what NR has done now is, you only transmit when absolutely needed, and in a way, the allocations or the over-the-air transmissions can be arranged in such a way that they can fit around some of the LTE signals. So the LTE signals take priority, and they always have to be there because you have to support legacy users that are out there that may be LTE only phones. But then the NR just sort of weaves around it and puts its signals around the LTE signals. And so a new phone that is NR capable understands that and can actually sort of decode the signal, ignoring the LTE part of it. So that's kind of how this flexibility is intentionally sort of put in place in the specifications.
Fantastic. So especially in the FR1 spectrum ranges, then this is really a huge benefit from almost a legacy operations perspective.
Yes.
Okay, cool. Next slide, please.
Before you go there, just the one important thing about this refarming is it's mostly, I would say, applicable to the low band FR1 spectrum, where again you don't have you have a spectrum crunch there. As you go towards the higher, mid band or FR2, this becomes less applicable.
Okay, cool. Next slide, please. So let's talk about maximum speed. So there's a maximum speed theoretically available, but at the end of the day, the operator has to have the spectrum and have bought it from the government in order to fit something. And also the configuration of the 5G network is important. So you have these theoretical 20 gig kind of at the tower, which is 20x times today's LTE, and a user experience of 100 meg or 10 times current LTE. But you know, let's talk about like the 5G network configuration with one example. So if I was to be building a network and I wanted to use wanted that full, like one carrier, 400 megahertz wide, if I was making the choice of a 400 megahertz channel requirement, what would be better from an engineering perspective? Would I want to do one 400 meg channel or say 4 100 meg channels? What would you do, and what would be the reasons behind it?
Yeah, so while we theoretically support up to a maximum of 400 megahertz of a single channel, in my view, it's better to actually do 4 times 100 megahertz. And the simple reason for that is that, you know, one single 400 megahertz will require essentially a contiguous chunk of that bandwidth being available. And so in many cases, that bandwidth is not contiguous and it's sort of fragmented. So what the ability when you go to a 100 megahertz component carrier and sort of have multiples of those, it allows you to sort of fit into your bandwidth availability much better. You lose something in terms of efficiency of utilization of the spectrum, because every time you have a 100 megahertz chunk, you can't actually occupy 100 megahertz. You have to occupy, let's say, 90 or 95 megahertz of that only. But the gain is the flexibility in deployment that you get. So I would say you pick typically the 4 times 100 megahertz configuration.
Okay, cool. Question from Christian. He's asking, does DSS work easily with TDD signals, or is it only for FDD type of spectrum use?
No, actually, that's a good question. It does work with TDD. There's no issue with that. I mean, DSS has many flavors, but one typical way is actually you time multiplex LTE and 5G signals as much as you can. And so there is no fundamental issue with DSS working in TDD. The only reason I said the comment earlier about, you know, mostly being applicable in FDD was because that's where the spectrum crunches, and so operators would not like to deploy, you know, necessarily or have to reform the spectrum. Whereas in TDD, many cases are like new spectrum allocations where they could define, you know, hey, this is one chunk of 20 megahertz for where we do LTE, and this is another chunk of, let's say, 60 megahertz or whatever, and that's where I do NR. So the need for mixing them is not as much, at least in my opinion, in the new bands that are coming up.
Got it. All right. Next slide, please. So as a note, the future configuration of the radio access network is called 5G standalone, where all the data and the control signals will be happening between the mobile device and the tower. And right now, because the United States is so large, we can't just instantly create the 5G network everywhere. So we have to maintain a lot of compatibility and leverage the LTE core networks in place. So we're doing something a little bit different in the United States, and I think a number of countries around the world are also taking the same approach. Next slide, please. And the radio access network deployment in here is using a mix of LTE and 5G, and it's called non-standalone mode, or 5G NSA. So let's Suresh, would you like to kind of unpack it and explain you know, how LTE and 5G are kind of friends together to deliver the 5G service itself?
Sure. Let me try to do that quickly. Um, Basically, if you have a 5G phone, a 5G capable phone now, what it'll always do is first actually act as an LTE phone. It'll actually do an attach procedure to the LTE base station. And in fact, once it does that and it announces its capability to be NR or 5G NR capable, the LTE base station or cell, as we call it, would actually ask it to measure other channels on NR itself. Then it would have to go through a sync procedure, searching for NR cells that are nearby. Once it finds that, it sends the measurement up, or the NR measurement actually, up on the LTE channel itself. And so all of the control plane processing is going over LTE initially. Once it's established that there is an NR, cell or a base station that the UE can use, then there's almost like a procedure which is known as X2, which is the protocol between a cell to another, a base station to another base station, where that user is switched to an NR channel. And so from then on, you can think of NR at that point as really like a supplemental data channel. So all of the basic data is flowing over LTE, but the user is using the NR as essentially like a data channel for pushing huge amounts of data. So that's kind of how the whole overall non-standalone operation works.
Fantastic. So in the little Venn diagram down there, um, when if there's only a 5G NR radio service, the mobile device won't have any service whatsoever. Is that correct?
Yes, so that's currently where we for the NSA mode. As we evolve over the years to the standalone mode, then of course NR would be working by itself. But currently, yes.
Got it. And so from an indoor perspective, if like for us for the enterprise RAM that Corning builds for indoors, the 5G that's deployed would be able to leverage the indoor LTE. Because of the propagation issues, if I was using indoor 5G and trying to do outdoors from a tower, I would have essentially all the same dead zones through my building if I didn't have indoor LTE services that I have today with LTE. Is that correct?
Yeah, that's actually quite correct. I mean, you will need LTE to be sort of blanket coverage, and then NR sort of rides on top of that. Yes.
Okay, cool. Next slide, please. All right. Trish is a subject matter expert on massive MIMO, and for those of you out there in the enterprise space, you know MIMO and use it every day on your Wi-Fi infrastructure, and from a innovation perspective, massive MIMO is extremely important to 5G in delivering the service. And Suresh, could you talk about massive MIMO and also maybe how it fits in and what's important about it in the lower frequency ranges like FR1, and then why it's important in the higher frequencies like FR2?
Sure, sure. MIMO essentially stands for multiple input and multiple output, and what that does is essentially use transmitting signals, different signals through multiple antennas, so that you're at one level intentionally causing interference, but in a very special way, such that the receiver, which is in this case, maybe on the downlink would be a user equipment or a UE, would be able to decode that. So it knows that these two signals have been intentionally multiplexed together, and so I can sort of undo it at the receiver. So what that does is, effectively is able to double the capacity or quadruple the capacity depending on the number of antennas that you're using. So that's the basic idea of MIMO. The idea of massive MIMO came out to looking at, as you especially start going towards higher frequencies, the antenna sizes and the apertures come down significantly. Just they're proportional inversely to the frequency. of operation. And so as a result, now you can apply lots of antennas that can actually do a combination of both MIMO as well as beamforming. So what beamforming does is essentially focus energy in particular directions. The analogy again that I like to use is if you think of a standard antenna that you have, on a Wi-Fi access point or whatever. If it's an omni antenna, it's kind of like a light bulb. It transmits energy in all directions equally, and so it's somewhat diffuse. Whereas on the other hand, a beamforming antenna is something that is like a torchlight, and that's actually a pretty correct analogy in the sense that in physically turning it, you can actually focus light and in a particular direction, but at the same token, you will not be able to see stuff around it, right? So it's just in the direction that you're focusing. So that's exactly what happens with beamforming, and that requires a fairly decent number of antenna elements that you can actually try to make these, as the pictorial here shows, highly focused beams that are, providing a lot of energy in a certain look direction, if you will, and not much else anywhere else. So it also reduces interference and so on. So in massive MIMO, you can trade off the amount of what's called a spatial multiplexing, that is the MIMO order, and beamforming, and with the same number of antennas that you have. So both of these techniques are used differently in the different frequency ranges. So in the lower frequency range, which is FR1, again, prime real estate, you need high spectral efficiency. You want to push more bits for the same amount of bandwidth. And so you try to do more spatial multiplexing, use the antennas for now, as the picture here shows. You can have two users that are spatially separated, and you can actually form two beams to them. This is called multi-user MIMO, such that both of them are being served and they don't cause interference to each other. So that's one of the key technologies in the lower parts of the spectrum that will be used to increase efficiency of air interface utilization. As you go towards as you go to higher frequency, beamforming becomes important because you want to get better coverage.
Got it. So we have a question from the audience on how big are the antenna panels. So I have seen the outdoor panels, which are meters across, or many feet across, and I've seen the millimeter wave where it's like an inch and a half by an inch and a half on a single piece of silicon. So the antenna panels, to Suresh's point, vary based on the frequency being supported by the antennas themselves. So when you say millimeter wave means the length of the wavelength. So the antenna length itself is it a full wave, like a full millimeter, or is it like a quarter wave, like a dipole or something? How long are those antennas on the millimeter wave?
So the whole panel, for example, at 28 or 39 gigahertz, an 8x8 array panel would be probably like 2 inches or so, 2 inches by 2 inches or thereabouts, or even.
Okay. Yeah. Great. All right. Next slide, please. All right. So this is ultra reliable and low latency communications, and this is something that's a evolving topic. One of the there's a couple different things here. There's improvements to 5G NR, where packets could be inserted into the air link at the front of the line for any kind of low latency type of device. There could be multiple connections to distributed radios, so that you have a lot of redundancy, and you have the potential for edge computing, and where maybe part of a cloud service that has to respond really fast to a attached device. Part of a cloud service is installed very locally to the radio access network, so that whatever activity is being performed has the fast response time that's demanded by the application that's layered on top of it. How from a 5G NR perspective, how does URLLC participate as far as getting to the front of the line? And can you kind of explain in like non-technical terms how URLLC is going to work with the radio infrastructure?
Yeah, sure. So one of the key sort of components of a radio technology or a radio access network is what's known as a scheduler. So a scheduler is the one that's responsible for scheduling packets to be transmitted over the air. So in a way, I think of it, again, talking of analogies, like a traffic cop. And so imagine that you have, let's say, a 4-lane highway, and then there's a 1 lane that's going the other way. There's a traffic cop in the middle, and cars are your packets essentially, right? So the traffic cop's job is, and that's the scheduler, is to let the cars go in a proper fashion and go over the lane so that they don't collide and so on. So in a way, one of the other jobs that the scheduler does, just like that of a traffic cop, would be to ensure that everybody gets a fair share of the access system. And so you want to make sure that the packets are scheduled correctly and nobody's getting starved of resources. What happens with URLLC now with 5G NR is that these are special packets that have a QoS tagging on them, that the scheduler knows that these have to go out as soon as possible. And so think of it as an emergency vehicle. When it comes along, you have to let that pass before anything else. So in that same way, this is kind of a privileged flow that the scheduler will actually put ahead of everybody else and actually transmit as soon as it arrives in the buffer.
Got it. So in your analogy, then the QoS marker is the lights and sirens on the emergency vehicle, huh?
That's right.
Okay. All right. Next slide, please. So this is the final of the 4 major technologies that are coming with 5G, and network slicing. Most IT people do this every day with VLANs on Ethernet, and carving up their networks with VLAN tags and that type of thing. From a 5G perspective, this is like way more sophisticated than a VLAN, but it's a useful analogy. So in this picture, that medical professional could have a regulatory HIPAA compliant slice that is supporting the radiology application and what's on that panel. There may be a different slice that's supporting mobile broadband for the device in her pocket, and there may be even a third network slice that's supporting the attached computer. That's also kind of below the radiology panel. So there's many things that are going to be possible with network slicing, but it's very emergent, and it's going to take a lot of network automation to make this happen in a seamless manner from end to end. I think there's a lot going on here. Suresh, can you talk about where this is going, and what the economic and business opportunities that are being kind of looked at by the operator community around network slicing?
Yeah, so this is actually, again, as you said, like a emerging area now. The idea is, how do you actually ensure sort of fully end-to-end with the radio access network playing in this space cooperatively to try to ensure that different services get the right sort of service level, kind of performance. And so you would actually not just, these things won't happen only at the core, but also get filtered down to the RAN itself, where you would actually do very dynamic radio resource assignments to ensure that certain types of traffic, so because there are various different quality of service requirements for different types of traffic. So some are very low latency, some require low jitter and so on. That you try to efficiently manage your compute infrastructure and the radio resources to actually ensure that all of those service requirements are met. And one of the interesting things that could be.
Can I interrupt for? Can I interrupt for a second?
Sure.
Can we forward to the next slide, because I think that it'd be a nice illustration to talk from. There we go.
Yeah. So exactly, these are different applications that you could provision for. So you could ask for a certain network slice that may require, certain agreements in terms of what kind of number of users, data rates, latencies, and all that you want to support, and a certain, on an average, a certain kind of a bandwidth reservation, and so on. And so once you do that, then it's up to the service provider to ensure that that kind of quality is met for that network slice. So it's as if you're having your own virtual RAN network. And I think the VLAN analogy is appropriate, but it sort of extends all the way to the radio here. And you don't, in theory, have to worry about what else is going on in the network, and you're guaranteed that kind of performance. And one of the things that could emerge from here is interesting ways to monetize this model, where you could have certain services that they're not network operators, but they could lease or rent parts of the network for certain types of for applications that they deserve, like if you have like an Uber service or whatever, you could actually have that kind of rented space, if you will, of the network that you can actually provide your access without being a full network operator.
Wow, cool. Well, this is going to be there's a lot of looking at over the next few years as it evolves. Okay, next slide, please. So just to summarize what we've talked about here today, 5G is not the first G, or it's his first G that's not just a faster radio network. There's three major benefits. There's the 8 technical goals that deliver to those 3 major benefits, and finally the 4 technology building blocks combined to meet those 8 technical goals. And what I'd like everyone to do that's listen to this today is, whenever you hear people talk about 5G applications, ask yourself, what of the 4 building blocks are possibly being used to deliver this service that someone's talking about? And in some ways, it's like, how does that differ from maybe LTE today? So there's quite a bit of new services on the horizon and things. And from an IT perspective, business users are going to come to an IT pro and say, I need advice on the network. I need advice on whether or not to use 5G for this. And in the other direction, from an IT perspective, you have to talk to the service providers on the cellular side, and ask them the deep questions, and make sure that whatever's happening for your business user is appropriately supported by that network. Let's see, and I have one kind of final question here, since we're at the 9:15 end. So in the future, developer and landlords should not expect tenants to hardware each desk or workstation. So we're going to a future where everything is wireless. I believe that for a lot of years, that the end user computing will have massive amounts of fiber in the ceiling to both Wi-Fi and cellular access, but the actual people will be untethered down in the office, so that you don't have to do moves, adds, and changes, and move any kind of physical services around on the IT perspective for the people, because they'll have their mobile phone and they'll have their Wi-Fi attached laptop. And for cell use in the buildings, you know, in many places, the landlord will do it as a fourth utility where it's a necessary system to have implemented in the building in order to, you know, attract tenants to move in or retain tenants that are already there. And in other places where the enterprise owns the building, you know, they're probably looking at putting something in because of the amount of complaints that might escalate up to the CIO about my mobile device not working. You know, we've talked to a number of you know, IT folks who don't want to officially support mobile devices on their Wi-Fi infrastructure, only because it doubles the amount of devices on the network and greatly increases the workload for IT if you end up supporting the last mile for everyone and you know, everyone that's on cellular. So we've you know, we've kind of heard from people that they're preferring to do cellular more as a practical operations response than just a technical you can or can't do it. It's more, I don't want to support it because I don't have the people on staff to do it. And with that, Elizabeth, would you like to close this out?
Absolutely. Thank you so much, Art and Cherise, for giving us and sharing your knowledge and making us a better technology community. Thank you for attending today. Please look on our website, see the light trainings for more and upcoming webinars, and there are more coming from Art, so be sure to take a look at that as well. If you have signed up and are here for Bixby credits, that will be automatically put into your email box, so look for that. Please give it about 24 hours to generate, and if you don't receive one, please just contact us at See the Light at Corning. Thank you again, Art and Sharish, for giving us this opportunity, and I hope everyone stays well and have a wonderful, wonderful rest of your week. Thank you.
Thank you. Thanks, Art.
Yep. Cheers. Bye.
Bye.